Equilibrium conditions. Equilibrium. Consider these objects. 1. A book resting on a table. 2. A hockey puck sliding across a frictionless surface with a constant velocity. 3. The rotating blades of a sailing fan. And 4. The wheel of a bicycle that is traveling along a straight path at constant speed. For each of these four objects, 1. The linear momentum p of its center of mass is constant. 2. Its angular momentum L about its center of mass or about any other point is also constant. We say that such objects are in equilibrium. The two requirements for equilibrium are then P is a constant and L is a constant. We are concerning largely with objects that are not moving in any way, either in transition or in rotation, in the reference frames from which we observe them. Such objects are in static equilibrium. Of the four objects mentioned at the beginning of this section, only one, the book resting on the table, is in static equilibrium. That is, its linear momentum p equals 0. If a body returned to a state of a static equilibrium after having been replaced from it by a force, the body is said to be in stable static equilibrium. Now, like this one. You move a little bit, it will come back. Okay. A marble placed at the bottom of a hemispherical bowl is the example. If, however, a small force can displace the body and end equilibrium, the body is unstable static equilibrium, like this one. You move more, it will falling down.
We'll use these objects to demonstrate three different types of equilibrium. This cube is in stable equilibrium. If it is displaced by a small amount, it returns to its original orientation. This sphere is in neutral equilibrium. It is stable in its original orientation and in any other orientation. This cone is in unstable equilibrium. If it is displaced by even a small amount, it falls over, instead of returning to its original orientation. This animation shows the weight that acts on the center of mass of each of the objects as it is tipped. This chair can be mounted on a sharp point at the top of this bar. The chair is now stable in all orientations and can be swung vigorously without tipping from support. Why is the chair so stable? Weights have been added inside the legs, which lowers the center of mass to below the point of support.
This toy clown is stable when placed on a tight string. Why doesn't the clown fall off the string? These weights shift the clown's center of mass to a point below the wheel. If we remove the weights, we shift the center of mass to a point above the wheel. Here's what happens without the weights. With its center of mass above the wheel, the clown is no longer stable.
There are many situations for equilibrium in the nature, Pisa Tower, and so on. The analysis of static equilibrium is very important in engineering practice. The design engineer must isolate and identify all the external forces and the torques that may act on a structure, and by good design and wise choice of materials, make sure that the structure will tolerate these loads. The requirements of equilibrium. 1. The vector sum of all the external force that acts on the body must be 0. Now, sigma F external equal to 0. That means, the linear momentum P equal to constant, because the change rate of linear momentum equal to sigma F. 2. The vector sum of all the external torque that acts on the body measured about any possible points must also be 0. Now, sigma torque about any point equal to 0. That means the angular linear momentum L equal to 0, constant to equal to constant. These are necessary but not sufficient conditions. You satisfy this question, this might not be equilibrium. The linear momentum P of the body must be 0. Now, you want to make it sufficient, the P must be 0. In other words, the velocity should be 0. Balance of forces. If sigma F equals 0, sigma Fy equals 0, sigma Z if balance of torque. Sigma tau x equals 0, sigma tau y equals 0, sigma tau z equals 0. Under this condition, there be chance be in equilibrium. If this is a two-dimensional, then we get fx equals 0, sigma fy equals 0, sigma tau z equals 0.
This meter stick is free to rotate on a pivot point at its center. Pegs at 3 different distances from the center can hold masses of either 100, 150, or 300 grams. If we put a 300-gram mass on this first peg, the stick becomes unbalanced. We can rebalance the stick by placing another 300-gram mass on the corresponding peg on the other side. To balance the stick, where should we put a 150-gram mass? We put it twice as far from the center as the 300-gram mass. Now we remove the 150-gram mass. Where should we place a 100-gram mass to balance the stick? We put it 3 times as far from the center as the 300-gram mass. Here's an interesting puzzle. If a person balances a meter stick on 2 fingers, with one finger closer to the end of the stick than the other, and then slides both fingers in towards the center, which side will the meter stick fall towards if it becomes unbalanced? The meter stick stays balanced the entire time, and both fingers end up exactly at the middle. Let's watch that again with one of the fingers starting even closer to the center. Again, the stick stays balanced. But if we try to reverse the process, the stick falls off. If we cover one finger with a rubber glove and coat the other with slippery chalk dust, will the meter stick give up this time and become unbalanced? Even with such a large difference in friction, the stick stays balanced. If a weight is added to one end of the meter stick and the demonstration is repeated, the stick still remains balanced, but the fingers meet at a different spot.